We're honored to have with us Dr. Berger. He is currently a professor of astronomy at Harvard. He got his PhD from Caltech and went on to become a Hubble Fellow and Carnegie Princeton Fellow at Carnegie and Mellon and Princeton, and is now at Harvard. Anyway, today he'll be telling us about the biggest explosion since the Big Bang, the mystery of gamma ray bursts.
Thank you. Okay. Let's see. We'll figure it out. Okay. So thanks for coming out. So today I'm going to tell you about gamma ray bursts, the biggest explosion since the Big Bang. And let me start by saying that I find gamma ray bursts fascinating for a variety of reasons. First of all, do I really need to say more than the biggest explosion since the Big Bang? Right? But beyond that, I think that gamma ray bursts are a very unique type of object, and I find them fascinating for two other reasons. First, I think gamma ray bursts represent the concept of scientific serendipity, discovering something that was never anticipated or predicted to occur. And this happens very often in science, but I don't think we often appreciate that sometimes just, especially in astronomy, just looking up at the sky, looking up at the universe, can teach us something completely new that we never anticipated. And gamma ray bursts, as I'll tell you, fall into that category. Nobody has ever predicted that gamma ray bursts should actually exist in the universe, and yet here we are talking about them. The other reason I find them fascinating is that gamma ray bursts push astronomy to its limits. So usually when we study objects in the sky as professional astronomers, we go to telescopes and we plan our observations months in advance, and we point the telescope at some object that is there tonight and will be there tomorrow night and a month from now and a year from now and probably a billion years from now. But gamma ray bursts only last for a very short period of time. So when we study gamma ray bursts, we have to do astronomy in a completely different way. It's kind of like working in the emergency room. Okay, so a gamma ray burst is discovered, and we have to take over telescopes and very rapidly observe this burst before it disappears. And you will see how exciting and sometimes frustrating and difficult that can be. Now, if this did not convince you that gamma ray bursts are interesting, then something like this should. Gamma ray bursts could kill all of us. Okay, tomorrow night, tonight. Fortunately, it's probably not going to happen, but gamma ray bursts are so powerful and so energetic, and the gamma ray radiation is potentially so damaging that you can see articles like this in magazines like Sky and Telescope, gamma rays of doom, or even claims that gamma ray bursts have caused some of the mass extinctions in the history of our planet. So if for no other reason, pay attention for this point. So before we start talking about what gamma ray bursts are, let's talk about what gamma rays are. I mean, after all, that's a part of the name. So gamma rays are a form of light. They're in fact the most energetic form of light that we know of. So of course the light we're most familiar with is visible light that we see with our own eyes when we look up during the daytime, or we look up at the night at the sky at night. We see stars and we see them with our naked eye. We look at visible light. Gamma rays are a much more energetic form of light. The wavelength of gamma rays is about the size of the nucleus of an atom, so they're very small wavelength, very powerful light. Now, what's interesting and important for our story of how gamma ray bursts were discovered and how they came to be an interesting source of study for astronomy is that gamma rays cannot penetrate the Earth's atmosphere. And that's good, because gamma rays are so powerful that if they could easily penetrate through down to the surface, they could cause severe damage to live tissue. But that means that if we want to study sources of gamma rays, we have to go above the Earth's atmosphere. Okay, so that means satellites. And that's the reason gamma ray bursts were not discovered in the 1400s or 1500s. They were discovered when satellites were first flown. So let's look back and look at how this story actually starts. So like a lot of good kind of mystery movies, the story of gamma ray burst starts at the height of the Cold War. It's 1963. The US and the Soviet Union have been testing larger and larger nuclear weapons, both on the surface, as you can see here, underground, in the atmosphere. And it was realized that this is going to cause damage to the planet, and this was not sustainable. So in 1963, the US and Soviet Union signed the Limited Nuclear Test Ban Treaty. And the point of the treaty was to limit nuclear tests in the atmosphere, beyond its limit, and most important for our story, including outer space. Okay, so here you can see a picture of President Kennedy signing this treaty. Of course, there was very little trust between the US and the Soviet Union. And so the Department of Defense decided that they have to develop a way to monitor whether the Soviets were complying with the treaty, whether they were actually testing nuclear weapons, especially in space, or maybe even on the surface of the moon. And the way they decided to do this is by launching these pairs of satellites called the Vela satellites. That comes from the word, the Spanish word velar, which means to watch or to guard. And these satellites were designed to detect the signature, or the most prominent signature of a nuclear test in space, which is a burst of gamma ray radiation that would come at the moment of explosion. And in fact, they launched these satellites not individually, but in pairs, with the idea that they could triangulate the direction of any nuclear test by looking at it from two different satellites. Okay? Just like we can tell the distance to objects with our two eyes, the idea here is that we'll have two gamma ray eyes up in the sky, looking all around to see if the Soviets were testing nuclear weapons. So the first of these sets of satellites were launched in 1963, and then additional ones were being launched every year to produce this kind of network of gamma ray satellites looking for nuclear tests. And then in 1967, the unthinkable happened. One of these pair of satellites detected a burst of gamma ray radiation. You can see it here. So you can see that for a few seconds there's nothing going on, and then there's this large spike of gamma ray photons coming into the satellite and then disappearing after a few seconds. This is exactly the signature these satellites were designed to detect. So this looked exactly like a nuclear test. And the people working with this data from the satellite at Los Alamos National Laboratory were really freaked out. This really looked like a nuclear test. And then they started finding another one, and another one, and another one. And by triangulating the distance and the location, they realized that there is no way that these could be nuclear tests. So a few years after the first ones was discovered in 1967, in 1973, these scientists at Los Alamos National Laboratory decided that it was time to release this information, to make it declassified, and to announce the discovery of bursts of gamma ray radiation coming from somewhere in the universe. And so they wrote this paper called Observations of Gamma Ray Bursts of Cosmic Origin. And this very short, innocuous paper started this whole field of study that I'm going to tell you about. Now, they made two interesting statements in this paper. First, that the durations of these bursts were variable. Some of them were only 1/10 of a second, some of them were maybe up to a minute or half a minute. But they also made the important statement that by triangulating using these pairs of satellites, they could tell that these bursts of gamma rays were not coming from the Earth or from the direction of the sun or from the moon. They were not coming from the inner part of the solar system. They had to come from somewhere further out, either in the outskirts of our solar system, or maybe in other parts of our galaxy, or maybe somewhere close to the edge of the universe. So here's a gallery of what these gamma ray bursts look like. In each one of these panels, you're seeing one individual gamma ray burst. And what you are seeing is the brightness in gamma rays as a function of time. And you can see that they look very different from each other, right? Some of them are very short and have one spike. Some of them are very long and have many, many spikes. In fact, I heard somebody at some point say, well, you know, if you've seen one gamma ray burst, you've seen one gamma ray burst. Okay? There's really no regularity to them. They come in all shapes and forms. Now, to give you an idea, these were the first gamma ray satellites that humans have ever launched into space. They were designed to find nearby nuclear tests. How is it that they found gamma ray bursts, things that are coming from the outer parts of our solar system, or maybe even much, much further away? How is it possible that our most primitive first-generation gamma ray satellites discovered gamma ray bursts? So let me give you an idea of how bright these sources really are, just so we can kind of understand what we're talking about. So here's an image of the entire sky that you would see if your eyes were sensitive to gamma rays instead of visible light. Okay, so what we're seeing here is very bright, the white region is very bright gamma ray radiation coming from our own Milky Way galaxy. And then as we move up and down away from the disk of our Milky Way galaxy, we see there are some sources of gamma ray light, but the gamma ray sky is pretty boring compared to what we see in visible light. Now let's see what happens when a gamma ray burst explodes or goes off. So here's the same image, and here's a gamma ray burst. Okay? So you can see the gamma ray burst up there at the top of the image. It gets brighter. And then for a brief few seconds, it outshines the entire universe in gamma rays. Okay? This one event, whatever it is, and we still don't know what it is, or at least at this point in the talk, we don't know what it is. It lasts for a few seconds, and it's brighter than the entire universe combined in gamma rays. Yeah, that is quite spectacular, and that's the reason that gamma ray bursts were the first thing that was discovered with our most primitive gamma ray satellites. Now, how bright are they? There's another way to look at it. So this plot is showing the ionosphere. The ionosphere is part of our own Earth's atmosphere, and the ionosphere moves up and down in the atmosphere during the daytime and nighttime. During the day, the sun kind of pushes the ionosphere down, and at night, the ionosphere floats up. And what you're seeing over there, that little spike, is the ionosphere getting pushed down by a gamma ray burst. Okay, so this is a gamma ray burst for a few seconds coming from somewhere in the universe, and it's actually affecting our own Earth. It's pushing down the ionosphere more strongly than the sun can do. Okay, so that gives you another sense of how powerful these events really are and why we're seeing articles like gamma rays of doom. Okay? You can imagine if the gamma ray burst like that was a little bit closer, what it could do to our own atmosphere. Okay, so 1973, gamma ray bursts are announced as a new class of discovery of a new class of astronomical objects. And the next 20 years are a big party. Okay, more and more gamma ray bursts are being discovered. Very little is known about what they are. And so astronomers are starting to come up with all different kinds of theories. Okay, all different kinds of ideas. What could they be? And by 1993, 20 years after they're discovered, a paper comes out that compiles all of the possible theories of what could be causing gamma ray bursts. And there are 135 different theories for what could be causing them. And at that time, there were only about 100 gamma ray bursts known. So there's more than one theory per gamma ray burst. Okay? It's not a good situation. Okay? But, so a lot of interesting thinking went into this problem. People got really excited. What is causing these kind of extreme objects? Now, what was driving a lot of these theories were the two basic things that were known about gamma ray bursts. One is that they have a very short duration. They only last for at most 10, 20, 30 seconds. And that they produce this extreme gamma ray energy instead of visible light or radio waves or something else. And so people started coming up with these ideas, and some of them centered on, maybe they're a new type of exploding stars, maybe they're flares that we see sometimes on the sun, but coming from other stars in our Milky Way. Maybe they had to do with annihilation of matter and antimatter. For example, people had the idea of, what if they are in the outer parts of our solar system? What if there are comets made of matter, normal matter, and there are comets made purely of antimatter? And once in a while, these comets collide. Then they would completely annihilate each other and produce a burst of gamma rays. Collisions of neutron stars, evaporating black holes, right? All kinds of very exotic theories. And even, remember, these satellites were designed to detect nuclear tests. So what if we're seeing nuclear tests on steroids from other planetary systems? What if we're seeing interstellar warfare? Whole planets getting blown up by nuclear tests? Why not? Right? So these are the kind of theories that were floating around, 135 of them. Now, why could astronomers come up with so many different theories spanning so many different types of objects and ideas and concepts and making up things like interstellar warfare? The problem was very common to astronomy. The problem was that we had no idea how far away gamma ray bursts were. The only thing that was known is that they're not coming from near the Earth or near the sun. But are they part of our solar system? Maybe somewhere where the comets are? Are they part of a Milky Way galaxy? Are they coming from other galaxies? Are they coming from the edge of the universe? Of course, with each one of these possibilities would accommodate a very different set of theories and a very different scale of energy. The further away they are, the more energy they require, and therefore they require a very different kind of power source. Now, why could we not figure out the distance? What was the big deal? Well, the problem was that these satellites were very good at finding gamma ray bursts, detecting them, but they were not very good at telling us exactly where they're coming from. So they could only tell us that they came from that part of the sky. Okay? And the region on the sky that an individual gamma ray burst could come from was much bigger than the size of the moon on the sky. So if we look at an image of that part of the sky, well, there are lots of sources there. So maybe the gamma ray burst came from that star, or that galaxy, or that star, that galaxy, or that collection of galaxies. Right? We have no idea. We have no idea where the gamma ray bursts come from, and therefore we don't know how distant the gamma ray burst is. So what was required was some breakthrough in understanding the scale, the distance scale, how far away gamma ray bursts are, and that would hopefully narrow down the number of theories from 135 down to 1. Okay, so how do we make progress? So people were very clever, and they said, well, there's an interesting test that we can make. We can at least answer the question, do gamma ray bursts come from inside the Milky Way or outside of the Milky Way? And how would we do that? So here's what our Milky Way would look like if we're looking at it. We're inside the Milky Way galaxy. We're part of this disk of stars in the Milky Way galaxy. So when we're looking at it kind of edge on. Now, if gamma ray bursts were coming from the Milky Way galaxy, they would all line up along the Milky Way galaxy. They would line up with where the stars of the Milky Way galaxy are, where the light is. So if we looked at a map of gamma ray bursts on the sky, this is what it would look like. Most of them would be lined up with the center of the map, and there would be very few gamma ray bursts up or down away from the center of the map. So that's a test, a clear test of demonstrating whether gamma ray bursts come from inside the Milky Way. So in 1991, NASA launched the Compton Gamma Ray Observatory, which was the first of the great observatories that NASA launched. The most famous of the great observatories that everybody's probably familiar with is the Hubble Space Telescope. But Compton was the first one of those satellites, and it was designed to study the sky in gamma rays at an unprecedented level. Much more sensitive, much more thorough than anything that was done before. And Compton included these detectors that you can see on the edge on all corners of the satellite that were specifically designed to find and locate gamma ray bursts. And it was so sensitive that the idea was that during its lifetime of about a decade, Compton would detect hundreds and maybe even several thousand gamma ray bursts and would make a map of what they look like on the sky. And we could make that test. So Compton started finding 1 gamma ray burst, and 2, and 10, and then 100. And at the end of its mission, it made this map of gamma ray bursts on the sky. Okay, so we're looking at this map. This is where gamma ray bursts come from on the sky. How many people think that this looks like the map that I showed earlier, that gamma ray bursts come from the Milky Way galaxy? Nobody. Okay, you guys are very smart. Okay. So it looks like gamma ray bursts come from everywhere in the sky. There is no preferred direction, right? You can't look at this map and say, oh, there are more gamma ray bursts coming from that part than from that part, or from the Milky Way or outside of the Milky Way. They seem to come from everywhere on the sky. So you would think, done deal, case closed, we figured gamma ray bursts out. Not so quickly. Okay, so 1995 rolls around, and this is after 4 years that the Compton Gamma Ray Observatory has been operating, and it made this map, and it found hundreds of gamma ray bursts. And the American Astronomical Society decides to organize a debate, a great debate, to celebrate the 75th anniversary of the 1920 Great Debate between Curtis and Shapley. And at that time, in 1920, the question was not where do gamma ray bursts come from, it was what is the size of the universe? So right around this time, Hubble, the astronomer, not the telescope, discovered these fuzzy little nebulosities on the sky, and he was suggesting that those are other galaxies outside of the Milky Way, what at the time was called island universes. And that position was taken on by Curtis. Shapley, on the other hand, argued that, no, these fuzzy little blobs were actually part of the Milky Way, and the Milky Way is the entire universe. Okay, so that was the debate in 1920. Is the Milky Way the entire universe, or are there other galaxies outside of the Milky Way? Now, we now know that Curtis won the debate, right? The Milky Way is just one galaxy out of hundreds of billions of galaxies, and the universe is much bigger than the Milky Way. So Curtis won the debate, and Shapley got to become the director of the Harvard Astronomy Department, where I am today. So you can see you can make mistakes and still get rewarded for that. Okay, so 1995 rolls around. There's an anniversary of this debate, but this time the question is, how far away are gamma ray bursts? And now we have two new protagonists. So Don Lamb from the University of Chicago, arguing that gamma ray bursts come from inside the Milky Way. They're all part of the Milky Way galaxy. And Bohdan Puczynski from Princeton University arguing that, no, gamma ray bursts are coming from much larger distances. They come from other galaxies. They're cosmological. They come from the cosmos. Now, all of you, just looking at this one plot that I showed before, this one map, agreed that there is no way that gamma ray bursts come from the Milky Way. So how could this argument take place? Right? It seems like the answer is obvious. Well, it turns out that around the same time that the debate was happening, astronomers made another interesting discovery, which is that there are neutron stars, these very small, compact, dense, exotic objects, flying out of the Milky Way galaxy at speeds of up to 1,000 miles per second. Okay? And so they would form this kind of spherical halo of neutron stars around the Milky Way galaxy. And what Don Lamb was arguing is that it's possible that these objects were producing gamma ray bursts, and therefore, even though most of the stars in the Milky Way are distributed along this narrow strip, these neutron stars come from everywhere in the sky, and therefore they would look very different in their distribution. Okay? So he made the argument, Bohdan Puczynski made the argument, there was a vote at the end, and it more or less came down 50-50. Okay? Astronomers could not make up their mind about how far away gamma ray bursts were based on this information, this map that was made by the Compton Gamma Ray Observatory. Okay, so it's 1995. It's now almost 30 years after gamma ray bursts were discovered, and the community was at a complete impasse about what's causing these sources. Okay, so it's clear that we need another breakthrough, something else. Okay, so this is one possibility. You take a big bowl of aluminum foil and you put it in a microwave oven and you say, well, let's see if that produces gamma ray bursts. How many of you have ever tried doing something like that? Okay, good. I did too. It's a lot of fun. Don't let your kids do it under any circumstances. But that was one possibility, okay? But, obviously we need something a bit more serious. So the idea came up that, just like when we set a fire, initially we have this initial phase where the fire is really bright. We have these bright flames. We can see it from very far away. And then after those flames die off, we get these glowing embers that last for a very long time. Right? The fire could maybe go on for an hour or two, but these embers can glow for a very, very long period of time. And they're not as bright, and they're not as intense in their light, but you could see them. So the idea was, what if something similar happens in a gamma ray burst? That the gamma ray burst itself is like the fire. It only lasts for a few seconds, and it goes away. But afterwards, there are these embers, this afterglow is the word we use for it, that lasts for a longer period of time. And maybe this afterglow doesn't just produce gamma ray light, maybe it produces X-ray light, and visible light, and radio waves. And if it does, then we have telescopes that are capable of detecting that signal and localizing it much more precisely than the gamma ray satellites can. So the idea became, we see a gamma ray burst, and we have very quickly to take a bunch of our telescopes and point it at that part of the sky where the gamma ray burst came from, and maybe we're going to catch this afterglow. And if we catch it, we're going to have a much more precise position for the gamma ray burst, and then we can see what's there. Is there a star in the Milky Way? Is there another galaxy? Who knows, right? But that would be the solution. Okay, so let me give you an example of how we do this. So I've been at Harvard for the past decade, and I've been running this kind of project. So here's what we do. We have a gamma ray satellite up in space, and it detects a gamma ray burst. And then we get a text message. We really do. We get a text message from the satellite to our iPhone, and then we call up all these different observatories around the world and in space, and we say, stop whatever it is you're doing. We don't care how important it is. Point at that part of the sky and look for this afterglow. Okay? So that's the part that's kind of like working in the emergency room, right? There's no time. There's no time to waste. We can't wait for tomorrow. We can't wait 6 hours from now. We have to do it right now. Okay? And you can imagine how popular that makes us with the rest of the astronomers. Right? Who wants to get a phone call in the middle of the night at 3 in the morning when you've been up all night using the telescope, telling you stop what you're doing, what I'm doing is more important. Okay, but in all seriousness, people actually do this because they realize that this is the only way we're going to solve this problem. We can't wait for tomorrow. We can't wait for next week. We can't wait for next year. And by the way, this is why I'm the only one who should have this cell phone turned on in this talk in case there's a gamma ray burst. Okay, so here's a little movie that NASA put together of how this works. So somewhere in the universe, there's a gamma ray burst. It gets picked up by one of these gamma ray satellites orbiting the Earth, and then the information is delivered to the ground. You see, the telescope is already moving, right? I mean, they were very obedient. And then we take images of that part of the sky, and we look for some afterglow that fades away and disappears. Now, as you can imagine, it doesn't come with a circle around it that says, this is where I am. You actually have to go and look and understand what you're looking for. But this is the basic idea and how we actually were hoping in the late 1990s to solve this whole mystery of gamma ray bursts. Okay, so the Compton Gamma Ray Observatory was very good at finding a lot of gamma ray bursts, but it wasn't particularly good at letting us know that it was finding them. It would find a gamma ray burst, and then a couple of days later, we would get a message from the satellite saying, hey, I found a gamma ray burst. But that would be too late. So this required a new satellite dedicated to this idea of delivering the information very quickly. And in 1996, the Dutch and Italians launched a satellite called BetoSax. And the idea was that this satellite could provide positions on the sky that are much more accurate than what the Compton Gamma Ray Observatory could. It wouldn't find as many gamma ray bursts, but it would find better positions, and it would announce them within a few hours. It would deliver this information down to the ground in a few hours, and then we can go and chase for this afterglow. And so the first detection of a gamma ray burst from the Compton Gamma Ray Observatory happened on February 28th, 1997. And what you're seeing here are two images taken by the satellite, this time not in gamma rays, but in X-ray light. And so you can see that on February 28th, there is a bright X-ray source right in the middle of the image. And then 3 days later, that source fades away. So this is the first detection of this afterglow in X-ray light. Okay? The first confirmation that this whole picture, that gamma ray bursts should be followed up by afterglows, was confirmed very shortly after the satellite was launched. Now, we're more interested not in X-ray afterglow, but in the afterglow in visible light. And the reason is that when we have an afterglow in visible light, we can pinpoint the location very accurately. Okay, so what I'm showing on the left-hand side are two images of that gamma ray burst, the same one I just showed you, now in visible light. And you can see that at the top one, there is an object right there in the middle with an arrow. And on the bottom image, it's gone. Everything else stays the same, but there's one object that disappeared. That's the afterglow. Okay? Again, it doesn't come with the arrow. Okay? It doesn't, the telescope doesn't tell you where it is. You have to look. But once you look and you start comparing all these sources, you can see that this source faded away. It disappeared. Now, I mentioned that the afterglow is not as intense as the gamma ray burst itself. It's not as bright. But it's also not faint either. So the movie on the right-hand side gives you a sense of how bright this afterglow is at visible light. So this movie takes several images of fading afterglow, and it just kind of makes a movie of how it evolves with time. And so you can see that it starts off extremely bright, and then it fades away and disappears. Okay, that's the afterglow. That's what we're looking for. Now, do you see all these fuzzy blobs around it? To the bottom right and to the top right. Those are entire galaxies. Okay, those are hundreds of billions of stars put together. And this afterglow, this one source, is brighter than those entire galaxies put together. Okay, so even though it's not as bright as the gamma ray burst itself, the gamma ray burst is as bright as the entire universe. The afterglow is only as bright as hundreds of billions of stars put together. Okay? But you can see from these images that now we can tell precisely where the gamma ray burst came from. The afterglow allows us to make a very precise position, and now we can go and study what's there. Is there a star in the Milky Way? Is there a galaxy? What is there? Okay, so how do we hope to measure the distance? So there's a concept of redshift, right? The universe is expanding, and objects that are further away from us are moving away from us at a faster speed, and that means that their light gets redshifted. It's kind of like when you have a train coming towards you, the pitch goes up. When it moves away from you, the pitch goes down. The same thing is happening here. As galaxies move faster and faster away from us, the light from them gets more and more redshifted. And so by measuring how much the light gets redshifted, we can measure the distance to those galaxies. So how do we do that? So we find this afterglow, we find this visible light, and now we don't just look at an image, we look at a spectrum of it. We take the light, we pass it through a prism, and we look at a spectrum, and we look for the signatures of different types of chemical elements that have very unique fingerprints, and we look by how much they're redshifted, and that tells us the distance to the gamma ray burst. So we can look at things like carbon and aluminum and oxygen and neon and magnesium, things that we know very well and understand very well, and we just ask how much are they redshifted and how far away did you get the gamma ray burst. So here's an example of one of these measurements. And this gamma ray burst is 12.1 billion light years away from us. Okay? So this is not inside the Milky Way galaxy. In fact, it's not even in some galaxy nearby. It's not even in a galaxy kind of far away. This is almost at the edge of the universe. Okay, this means that the light you're looking at in these images that I showed you and in this spectrum traveled for 12.1 billion years before it got to our telescopes. Okay, this gamma ray burst happened when the universe was much, much younger than it is today, maybe 10% of the age of the universe today, and that light has been traveling to us for all these billions of years, and then we had a window of opportunity of only a few hours to catch it before it disappeared. Just to get a sense of the scale of this problem. But essentially what this is now telling us is that of all of these 135 different theories, we can scratch out maybe 130 of them, or 132 or 133, because the amount of energy that's required to produce a gamma ray burst is the equivalent of taking the entire sun, taking Einstein's famous equation, E equals mc squared, taking all that mass in the sun and converting it all into energy in 1 second, and that would be the energy of a gamma ray burst. Okay, that's an enormous amount of energy. The sun will take 10 billion years to produce all of this energy. A gamma ray burst does it in 1 second. So how do we actually think this happens? What kind of object is powerful enough to produce that much energy so quickly? Well, we think that the only kind of objects that can do this are black holes. And in fact, when we're seeing a gamma ray burst, what we're seeing is not just one of the most extreme objects in the universe in terms of its brightness. Every single time when we see a gamma ray burst, we're seeing the birth of a black hole. Okay, so think about that for a second. We're actually seeing the birth of black holes. And that is really the only explanation for what can produce so much energy. Okay, so far I've talked about gamma ray bursts as if all of them belong to one category of objects. It turns out that there are actually two kinds of gamma ray bursts. They are the short bursts and the long bursts. One thing you need to know about astronomers, we're not very imaginative with names. So we look at the distribution of how many bursts have what duration, and we see that there are two groups, long and short, and so we call them long and short. So the long ones last for more than about a second, and the short ones are shorter than about a second. Okay, so not all gamma ray bursts are exactly the same. So if there are two types of gamma ray bursts, does that mean that these gamma ray bursts are caused by two different kinds of objects? No, maybe all of them are produced by the birth of a black hole, but how was that black hole born? Maybe it was born in two completely different ways. Okay, so what's actually producing gamma ray bursts? What's giving birth to these black holes? So we think that there are two main ways of actually accomplishing this. One is the death of the most massive stars. Okay, so these are stars very different from our sun. They weigh probably as much as 100 times more than our sun, and their life is very short. Our sun is going to live for 10 billion years. Okay, we're about halfway through its life now, about 5 billion years. It's got a long way to go. These very massive stars only live for a few million years. Okay, so I always like to think about them as the rock stars of the universe. They live fast, they die young, and they die explosively. Okay, so that's the idea, is that we have these very massive stars. They live for a very short period of time, and at the end of their life, they're not just going to fizzle away like the sun will. They're going to explode. And when they explode, they're going to leave something behind. And what they're going to leave behind is a black hole that produces a gamma ray burst. So what I'm showing you in these two movies, the one on the left is an actual computer simulation of the death of a star, showing how it can produce a black hole and this outflow of radiation that can produce a gamma ray burst. And then the movie on the right is more of an artist's conception that kind of looks a lot cooler than the one on the left. So that's one idea of how to produce gamma ray bursts. Now, there's another way. There are these objects that I alluded to before, these neutron stars. So neutron stars are the leftovers of supernova explosions. They weigh about the mass of the sun, maybe even twice as massive as the sun, but they're about the size of the city of Montreal. Okay, so imagine taking the sun, compressing all of that into the size of the city of Montreal. These are very dense objects, very extreme. Now, many times they're born in pairs. And over time, they orbit each other, and the orbit gets closer and closer and closer, and eventually they can smash into each other. So now you have Montreal smashing into, I don't know, Toronto, each one weighing as much as the sun. You can imagine that that's going to produce a lot of energy. In fact, that merging of two neutron stars leaves no other outcome than the formation of a black hole. So that is potentially another route to making gamma ray bursts. So again, the movie on the left shows the merger of two neutron stars into a black hole, and the one on the right is the artist's conception. Okay? Once again, the artist's conception is so much cooler. Okay, so two different ways of making black holes that can produce gamma ray bursts, and we have two types of gamma ray bursts. What a coincidence. So how do we test this idea? Well, remember, if gamma ray bursts come from these very massive stars, because these stars live so fast and they die so young, that means that they explode while they're still, so to speak, in the cradle. So they're going to explode and produce these gamma ray bursts when they're in the exact same environment when they were born. They had no time to move outside of the house, right, go to college. They just explode right away. So where would we find them? We would find them in star nurseries, in areas where stars are being born. These very massive stars would very quickly live their life and die and explode and produce gamma ray bursts in those same environments. So where do star nurseries happen? So here's a beautiful picture of a spiral galaxy. This is what the Milky Way would look like if we could kind of fly outside of the Milky Way and look at it from the top. And you can see that along these spiral arms of the Milky Way galaxy, there are these bright knots of light. Those are star nurseries. Those are places where new stars are being born all the time. And that's where gamma ray bursts would happen if they came from these star nurseries. So here's a picture taken with the Hubble Space Telescope of a galaxy that had a gamma ray burst in it, much further away than the one on the left. And the circle marks the location where the gamma ray burst came from. And you can see that it comes from the spiral arm of this distant galaxy, right? It just looks like a further away version of the picture on the left. Another place where these star nurseries occur frequently is when two galaxies merge. So galaxies actually live very far apart, but once in a while, two galaxies can collide and merge together. And when that happens, it makes for these kind of beautiful pictures. But again, in the right picture, taken with the Hubble Space Telescope, all these very bright, kind of bluish nuts of light are areas where new stars are being born because of the collision of these two galaxies. So if gamma ray bursts came from these star nurseries, then we would expect to find them in these kind of train wreck collisions of galaxies. And once again, here are images of gamma ray bursts. And you can see that they indeed come from these galaxies that look like they're in the process of merging together and colliding together. Now, these are the long duration gamma ray bursts that I showed you. So it seems like the long duration ones, the ones that last more than a second, maybe even up to several minutes, come from these very massive stars. Now, what about the short duration gamma ray bursts, the ones that last for only a few milliseconds, maybe up to a second? Well, if those come from the mergers of these neutron stars, that process of taking two neutron stars and bringing them together takes billions of years. It doesn't happen overnight. So by the time they collide together and produce a gamma ray burst, everything else in the galaxy would have stopped happening. All the stars would have, the massive stars would have died away, right? They only take a few million years to live their life. So after a few billion years, we'll be left with a galaxy that's full of just old stars. And we call these galaxies, they're called elliptical galaxies. They don't show these spiral arms, and they're referred to as dead galaxies. Not a very nice name, but that's what they are. So it would be something like this, a galaxy that's composed only of old stars. Well, here are images of galaxies that had short gamma ray bursts in them. And you can see that that's what they look like. They just look like these spherical blobs of light without spiral arms. Okay, they look like these dead galaxies. So it looks like the short gamma ray bursts are coming from very different environments and are produced by very different types of sources. They're produced by these collisions of neutron stars. So it turns out we can come up with two different ways of making gamma ray bursts, and both of them happen in nature, giving us our two different types of gamma ray bursts, the short and the long. Okay, so you can say, well, that's great. So what have gamma ray bursts done for us recently? Anything exciting going on in this field? Now that you've solved everything? Well, it turns out that gamma ray bursts can help us answer two extremely mysterious questions about the universe that astronomers have pondered for a long period of time. So remember, these short gamma ray bursts come from these collisions of neutron stars. Now, when these two neutron stars collide, most of the material that was part of the neutron stars goes into forming this new black hole. But as you can see in this movie, some of it just flies away. And that material is made out of neutrons, right? These are neutron stars. So the material that's flying away is made out of neutrons. And when you take a lot of neutrons together and you just fling them out into space, they find each other and they form new elements. And in particular, they form very heavy elements, or so the theory goes. So one of the key questions in astronomy, and one which we should take very seriously as human beings living on a planet like Earth, is where did all these elements that we see in the periodic table come from? What actually produced all these elements? So we know that the lightest elements, hydrogen and helium, were formed in the Big Bang itself. And then slightly heavier elements, things like carbon and oxygen, which are extremely important for life, things like iron and titanium and nickel, were produced in supernova explosions. But then we have all of these very heavy, very rare elements, things like gold and platinum and uranium, things we care about, right, that have an impact about life, whether it's for our jewelry, whether it's all the rare earth elements that go into our cell phones and allow us to connect to Facebook. Where did these elements come from? Well, we have no idea. We have theories, but we have no idea. And it's in fact one of the most interesting questions in understanding the periodic table is where did half of the elements in the periodic table come from? What kind of process produced them? So, a few years ago, I was observing one of these short gamma ray bursts, and trying to find out if there is a way of demonstrating that in that collision, all these neutrons that were flying out were forming these very heavy elements. And the signature of that formation process is the production of infrared light. Okay, so if this was actually happening in gamma ray bursts, in these short gamma ray bursts, we would see this flash of infrared light that was happening at the time when all these elements were being formed. So I was thinking, why don't we look at one of these gamma ray bursts, take the Hubble Space Telescope, and very quickly swing it over to the position of the gamma ray burst and see if we find that little faint signal of infrared light. And that's what I'm showing you in those images. So these are images taken with the Hubble Space Telescope. The ones on the left were taken within a few days of when the gamma ray burst happened. The ones in the middle were taken about a month later. And the ones on the right are just taking the one on the left and subtracting the one in the middle. So everything that's constant would disappear, and everything that was new would look like a source. And you can see that in that circle on the bottom right, there is a source of infrared light. Okay, and that circle is not, I didn't just put it there, that's the position of the gamma ray burst. So at the position of the gamma ray burst, there's this excess of infrared light. And that excess of infrared light is the signature of the formation of these very heavy elements. Now we can look at the brightness of it and ask, so how much of these elements was produced? How much gold was produced in this? You know, let's talk business here, right? How much gold was produced in this gamma ray burst? Well, several times the mass of the Earth. Okay, so one gamma ray burst produced several times the mass of the Earth in gold. Okay, so we put out this paper and we put out a press release, The Origin of Gold Discovered. This is the first time I got phone calls from the Wall Street Journal. They wanted to know, so how much is it worth? And I was trying to calculate, the price of gold is $1,000 per ounce, and we have several times the mass of the Earth. And then I realized, if we just dumped on the market several times the mass of the Earth in gold, it would be worthless, right? So luckily that doesn't happen. But I think what we've seen here for the first time, and we are now trying to follow up on this and find more cases like this, is the signature of the formation of the heaviest elements in the universe. Okay, so Carl Sagan said many, many, many years ago that we are all star stuff, right? We're all made of stuff that was produced in stars. So I would now add to it a corollary that says that all of our jewelry is actually colliding star stuff. Okay, it's all coming from these neutron stars. So when you go home tonight, look at your gold ring or your gold earrings and think about this. These came from the collision of two neutron stars that made a black hole that made a gamma ray burst. Okay? And in all likelihood, the earring on your right ear and the earring on your left ear came from two different collisions of neutron stars, not from the same one. Okay. Anything else exciting? I don't know. Yeah, so let's see. One of the other big questions in astronomy these days is how did the universe evolve from the very beginning, from the Big Bang to where we are today? And so astronomers have been working extremely hard using the biggest telescopes on the ground, using the Hubble Space Telescope, to slowly look further and further back in time and understand how did stars form, how did galaxies form. And we are now today about 13.5 billion years after the Big Bang. And we've managed to come up with a general story of how this process happens, going back all the way to about 1 billion years after the Big Bang. And then we enter this part of the evolution that we call the Dark Ages. Now, we call it the Dark Ages for two reasons. One is that during this period of time between the Big Bang and about 1 billion years later is when the first stars and galaxies in the universe actually formed. So before that time, the universe really was dark. There was no light. There was no source of light. There were no stars. There were no galaxies. And then at some point, the first stars formed and the first galaxies, and then from there they evolved to where we are today. The other reason we call it the Dark Ages is because we have no idea what's going on there. So for us, it's the Dark Ages. We are clueless about what's happening. So it's a big question mark, the first billion years in the evolution of the universe. That's quite a long period of time, and we want to understand what's going on there. Now, we can make computer simulations of how the universe evolved from the Big Bang to where it is today. That's a lot of fun. You can make these beautiful movies. But they're computer simulations. What if they're wrong? What if the information we put in is incorrect, and so we're not getting the right picture? What we need is actual data, actual observations. Now, the challenge is that as we look at objects further and further away, further and further back in the history of the universe, they become dimmer and dimmer and dimmer and more difficult to find. So gamma ray bursts could actually help us. Remember that a gamma ray burst, a single afterglow from a gamma ray burst, is brighter than an entire galaxy. So we could potentially see gamma ray bursts all the way into the dark ages. And in fact, if some of the massive stars that formed in the very first generation exploded and made gamma ray bursts, we might ultimately be able to find the first stars in the universe. Okay? So that's the goal. So the idea is that we find some gamma ray burst extremely far away in the middle of the dark ages, and that light has traveled to our telescope for a very long period of time. And we can detect it, and we can pinpoint where it came from. And if we find enough of them, we might eventually see an edge to where they come from. And that edge will tell us when did the first stars in the universe form. It's a very interesting question. Okay, so until a few years ago, so before I came to Harvard in 2008, the most distant gamma ray burst that we knew about was right on the edge of the dark ages, about 1 billion years after the Big Bang. So that wasn't particularly interesting. And over the last few years, we've worked extremely hard to try to find gamma ray bursts that are even further away. Okay, so what I'm going to show you next are the most distant gamma ray bursts we've ever seen, which in fact are the most distant objects that we know about in the universe. Okay, are you ready? All right, that's what they look like. Man, not particularly impressive, right? Okay, so these are images of the afterglow light from 2 gamma ray bursts. The one at the top happened only 630 million years after the Big Bang. The one on the bottom happened only 525 million years after the Big Bang. Okay, so if we go back to our diagram, and there's another one that I didn't have space to show you the pictures of. We now have 3 of these gamma ray bursts that are square, right square in the middle of the dark ages. Okay, so as I said, these are the most distant objects that we know about in the universe. And they're not entire galaxies, they're just one individual star blowing up. Yeah, which is kind of amazing. Okay, so we know that these gamma ray bursts they exist in the dark ages. Can we do something useful with them beyond just looking at them, looking at pictures? So one idea is if we have them right there in the middle of the dark ages, the light from these gamma ray bursts is going to travel through the entire universe in order to get to us. So we can study that light in detail to see what is the universe composed of all the way between where the gamma ray burst happened and where we are today. So think about an analogy of you're sitting in a dark room. For you, that's the dark ages. And for a brief few seconds, I shine a flashlight. Okay, so in those few seconds, if you can study the light from this flashlight in detail, you can look at the contents of the room around you. Does it have chairs? Does it have tables? Is there a sofa? The idea is to do the same with the universe. We have this flashlight that shines for a very short period of time, maybe only a few hours in visible light. And in those few hours, we can ask, what is the universe composed of, all the way between us and the gamma ray burst? How much carbon is there? How much oxygen? How much iron? How much gold? Now, in order to do that, we need a new type of telescope. We can't use the telescopes that we have now. They're just not big enough. They're just not sensitive enough. And so we are building next generation telescopes. And the one I'm particularly excited about, because Harvard is a partner in this project, is called the Giant Magellan Telescope. So I told you, astronomers are not good with names, right? They're not very imaginative. So these days we have the Magellan telescopes in Chile. So this is a bigger one, so we call it the Giant Magellan Telescope. So this is an artist kind of drawing or architect drawing of what this telescope will look like. And the construction for it is actually going on right now. Each one of these 7 mirrors is the size of the world's current biggest telescope. Okay, just to give you a sense of scale. Each one of these is 10 meters across. Okay, I love being in Canada. You can talk in meters. So imagine it's a substantial fraction of the size of this room. Okay? And so we are going to build this telescope for a variety of reasons, but one of them is to be able to collect enough light from these extremely distant gamma ray bursts so we can study them in detail. Okay, this just shows the scale of the current biggest telescope. Okay, so this is one of these mirrors, just one of them. And these are normal sized people. Just to make clear, yeah. So this is just one out of the 7. So this is going to be an enormous telescope. It will collect light and be able to study the faintest objects that we can see all the way at the edge of the universe. And in particular, my excitement is that it will allow us to dissect the light from these gamma ray bursts, the first gamma ray burst in the universe, in great detail, and tell us when did the first stars form, what is the universe composed of, all the way to its very beginning. Okay, so I hope you enjoyed this journey through, about 40 years or so since the discovery of gamma ray bursts. And again, just to reiterate, this discovery was completely accidental. Right? It was discovered by satellites that were launched to monitor nuclear tests. Had nothing to do with astronomy. They discovered what I think are some of the most fascinating objects in the universe. And for the past 40 years, we've been kind of chasing this mystery, and we are starting to answer some of the important questions. And the next step is not just to understand what gamma ray bursts are, but to use them as one of the most powerful tools we have to study the beginnings of the universe. Thank you. Yeah, so the question is, do we see enough gamma ray bursts? Do they occur often enough that they can account for the abundance of these very heavy elements? And the answer is yes. So we know how often they occur, and we know how much of these heavy elements they produce every time they occur. When we combine that together, we can account for essentially all the gold we see in the Milky Way galaxy. Yes?
Were the oldest gamma ray bursts of a given type short or long?
That's a good question. So the question is, the oldest gamma ray bursts, are they long or short? All of the ones we've seen so far are the long ones. And I think part of the reason is not that the short ones don't happen at these very large distances. The short ones are not as powerful as the long ones. And so we can see the long ones further away than the short ones. Yes?
In the beginning of the presentation, you compared the gamma burst to a flame and the afterglow to embers. If the burst is pure, what is the afterglow composed of?
Excellent question. So the question is, the gamma ray burst is a burst of gamma ray radiation, and what is the afterglow actually composed of? So what we think is happening to power this afterglow light is that the aftermath of the explosion of this object slams into all the material that was around that system when it exploded, and that collision between the material from the gamma ray burst and the environment is what powers the afterglow radiation. Yes, all the way in the back.
The three that were observed at the 630 were they in the same area of the galaxy? Like, I ask this question because does it help us establish what part of the universe, that we're in? Like in the middle, are we on the edge? Like, how does this help us?
Okay, good question. So the question is, are these very distant gamma ray bursts, do they all come from a specific patch on the sky, and what does it tell us about where we are in the universe? So each one of them came from a completely different direction, completely different random direction. And I think that's consistent with our picture that wherever we look on the sky, whatever part of the universe we look at, essentially looks the same. And that's due to the just expansion of the universe. So it all looks like it's moving away from us, but we're not really in the center of it. Anywhere you would sit in the universe, it would look like the universe is moving away from you. Yeah.
So do gamma ray bursts have to be associated only with black holes? Can it not be by hypernovas or like supernovas? And in the case of hypernovas, supernovas, you see gravitational waves. So has there been any association between gamma rays and gravitational waves?
Okay, those are loaded questions. Okay, so the question is, are gamma ray bursts associated just with the formation of black holes, or they're associated with supernova explosions, or maybe with sources of gravitational waves? So the long gamma ray bursts, when they happen, in addition to the gamma ray burst, we also see a supernova explosion. Okay, and that's because those are massive stars. And whenever a massive star dies, whether it produces a gamma ray burst or not, it also makes a supernova. In terms of gravitational waves, since the short gamma ray bursts come from the collisions of these two neutron stars, we expect that they will produce gravitational waves. Now, as all of you probably heard, gravitational waves were finally actually detected 100 years after they were predicted. And the hope is that over the next few years, we will actually see the detection of a gravitational wave and a gamma ray burst at exactly the same time. And that is a prediction of this whole idea that the short gamma ray bursts come from these collisions of neutron stars. So I think this will happen shortly. It will be in the New York Times, so just keep your eyes on it. Yes?
Is there a way to, with one of those new theories, you say that the bursts, after that you see after effects, but with the right theory, can we predict before effect, meaning that there is events that will predict or tell you that they may happen to be maybe in half an hour in a gamma ray, and you don't need to rush.
Yeah, so the question is, can we predict that a gamma ray burst is about to happen and be prepared for it instead of running around like chickens with our heads cut off? The answer, unfortunately, is no. We have not found any obvious way that will tell us where the next gamma ray burst is going to come from. Now, one thing I didn't mention is that with our current satellites, we're finding about 2 gamma ray bursts per week. Okay, so there's one happening about every 2-3 days. Somehow they all seem to happen on the weekend, don't ask me how. But there is really no predictive way of saying the next one will come tomorrow at 10 p.m. from that direction on the sky. We really have to just look for them and wait and be ready to jump into action. Yes?
Towards the beginning of the presentation, you had the Milky Way picture and then the Compton, all the data was spread out with different colored dots. What were the different colors? What were they from?
Okay, so the question is, in this diagram that showed the locations of all the gamma ray bursts on the sky being uniform, there are different colors. The colors were indicative of how bright the gamma ray bursts are. But even if you look at different brightness, and which means different colors on this plot, they all look like they're uniform in the sky, and we now understand that it's because they come from everywhere in the universe. And there is no preferred direction in the universe. Yes?
Are gamma ray bursts, are they hazardous to astronauts?
Okay, so the question is, are gamma ray bursts hazardous? So they will be hazardous to all of us if one happens sufficiently nearby.
Outside the atmosphere.
Outside the atmosphere, so none of the things we've seen so far are hazardous. We think that if a gamma ray burst happened close enough, maybe a few thousand light years away, it could potentially be hazardous, both to somebody in orbit or on the ground. Fortunately, gamma ray bursts, because they're so extreme, they're also very rare. So in the Milky Way galaxy, a gamma ray burst happens maybe once every 10 million years. So the chance that we'll have one nearby anytime soon is not great. So you can go home tonight.
So like 1 or 2 questions?
Okay, let's see. Yeah.
Why did you say it takes hours to detect a gamma ray burst from the central satellite? Does it need to flash it to detect right away?
Sorry, I didn't catch the
Why
first
does
one.
it take hours to detect a gamma ray?
Oh, so the question is, why did it take hours? So the detection itself was immediate. The hours was the time it took the satellite to then send the information down to the ground. Now, this is no longer the case. With our current generation of gamma ray satellites, we get a text message within about 10 seconds of when the gamma ray is detected. Okay, so it's really directly satellite to iPhone. Okay, let me see. Somebody didn't ask. Yeah, all the way in the back there.
I have your illustrations like show when you're there, show like streams coming out.
Yes.
Yeah, those cameras.
Good question. Okay, so the question is, what are those streams coming out? So yes, the idea is that these gamma ray bursts, actually, the gamma ray emission that comes out doesn't come out in all directions uniformly. It comes out in these very narrow cones of light. Okay? Now, you can come downstairs afterwards and ask me how I know that, but I'm not going to go into that now. But this has a very important implication. It means that if the gamma ray burst is pointed somewhere else, we don't see it. In fact, what we know is that these cones of light are so narrow that we only see 1 out of every 100 gamma ray bursts. So when I said there are 2 of them happening every week, those are 2 where this cone is pointing at us. There are another 200 that we don't see, luckily, or we would never sleep. And so there are more gamma ray bursts in the universe than the ones we just see.